Topographic maps are maps that show the shape of the land, the topography. It takes a three-dimensional images with hills and valleys, and then converts it to a two-dimensional image. It just takes a little practice figuring out how it works. All right. First, you start with the information, and you plot it on a map. In this particular case, we've got a map of the United States and several different locations. Each of these locations represents a weather station. The weather station took measurements of the local air pressure. It's also called the barometric pressure. It's very important to the weather. And then they sent it to whatever localized computer was going to compile it into a map. And so we see here that at this particular time, Northern Virginia had an air pressure of 1,012 millibars. Up in Maine, it was 1,016 millibars. The air pressure is something everywhere because there's air everywhere. So this is called a field of data. Okay? You can have this sort of field of data with temperature, air pressure, elevation, wind speed, number of Facebook posts, anything you can think of that you could plot on a map, and a number of things you can get put together like this. The problem is that the raw numbers are rather confusing to look at, so we have to do something with them. What we do is we create ISO lines. ISO means same. So they're lines that connect points of the same value. Basic ISO line shows whatever the local field value is. An isotherm, therm is another word for heat. So, same heat, it's the same temperature. Isobar, bar is short for barometric pressure, so they're lines of equal air pressure. Contour lines show lines of equal elevation, which is height above sea level. So let's do that with this map. Let's draw some lines. In this case, since it's air pressure, the name of them would be isobars. So, like for instance, right here where my keyboard happens to be is 1,012. So what I do is I connect it to the other 1,012s. And I keep going. And I've got most of a circle. I could connect these, but it goes off the edge of the map. And the rule is that you don't want to go off the edge of the map because you don't know what's happening here. We've got Canada here. Who knows if the air pressure could need to go up that way or down lower. We don't know how to draw the line here, so we won't. Okay? Here we've got 1,016. Locally, we've got a number of 1,016s. And sort of trace kind of along the edge there. We can't jump across here. No way. But we could try and do a line this way. And we can't jump there. It leaves us some 1,008s. We could connect those lines. Over here, got 1,020s. And we can connect these 24s and 16s. So now we've got something that's a lot easier to understand. We've got a pattern. Here's our pattern. Notice we have two circles. Well, if we take a look at these circles, we notice something about their values. You ever seen 8 highs and lows listed on a weather map? That's where these come from. Over on here on the left, we have a high, because this is the highest pressure in the area. It's all 1,024. So this is a high pressure. Over here, we have a low pressure. That's all 1,008s. They're the lowest things in the area. This actually helps us a lot with weather. I usually think happy highs and lousy lows. A low pressure brings with it storms, and a high pressure is clear skies. So if you're trying to have a picnic, you don't want that lousy low showing. You want the happy high. Now, we can do maps with other information as well. This one, actually these two, are two versions of an isotherm map. Therm means heat, so these are temperatures. These areas submitted their local temperatures, like Myrtle Beach, 81, and then someone drew contour lines, well, isotherm lines, to connect the points of equal temperature by the 10s, 60s, 70s, 80s. And then, this is the type of map you usually see on the Weather Channel. They colored it in. Everything between 90 and 80, they did a pale orange. Anything 90 and above, like down here in Montgomery, they made a deeper orange. Anything between 70 and 80, yellow. And thus, you get this nice, easy to read map where you know it's real hot down in Mexico and the rest of the southeast, and it's cold up here by North Dakota. And here we have another isobar map. These are all barometric pressure. So we've got, a nasty little low here. 996 is kind of low, so it's going to cause some tough storms. Now the topographic maps that are the main point of today. These have contour lines. These brown lines here, they're all contour lines. They show you elevation. Every point along a particular line is the same elevation. On one side it's going to be below that elevation, and on the other side it's going to be above that elevation. Elevation is vertical height above and below sea level. The question is, though, why sea level as a reference point? Well, we use sea level as a reference point because the sea level is the same everywhere. We want to all use the same zero, so we can measure the height of a mountain here in Virginia off of sea level, and they can measure a height of a mountain in France above sea level, the height of a mountain in India above sea level. And since we're all measuring off the same thing, we can say definitively that yes, Mount Everest is the highest point in the world. So with these maps, we take a three-dimensional view, like this one at the top. We've got two hills, a river between, a little bay, and this is called a spit, where the land juts out a bit from into the ocean. We make a two-dimensional view. You look straight down from above, and we've got two hills, gentle on the left, gentle here, steep here. And you see that in the lines. You can see the spit, the bay, and the river. When you're reading contour lines, you'll have a map, and you have to know what you're counting by. Because notice, not all of these have numbers on them. This one says 700, this one says 800, but you have no idea what these lines in the middle are. Because if you look at a contour map, usually the lines are so close together, if you tried to put all the numbers on, you'd be totally lost. So you need to be able to figure out what the elevation of B is. You need to know what we're counting by. And that's what the contour interval is, the difference in elevation between any two contour lines. To figure it out, you look at the ones that are labeled, and you subtract the difference in those two. So 800 minus 700. 800 minus 700 is 100. Excuse my bad handwriting. And then you divide by the number of spaces between the contour lines. We've got 1, 2, 3, 4, 5 spaces. 100 divided by 5 is 20, which means that we are counting by 20s. So if this, at point A, this is 700. This next one would be 20 up closer to 800. So 720, 740, 760, 780, 800. Yay, we counted right. 2, 4, 6, 8, 10. D then must be above that at 820. Down here, this is 720, 700. This one must be 680, 20 less. So we know A is 700, B, everything along this line is 740, everything along the line is 760. Ooh, C is not on a line. What do we do? Alright, what we do know is that it's not 760 and it's not 780. It's somewhere in between. It could be anything from 761 to 779. You might call it 770. That's fine. Anything in this range would be an acceptable answer. All right. I think of these contour lines kind of like stairs. Each time you take a step, they're an even tread, right? Up, up, up. When the stairs are really close together, it's really steep. When it's stair, 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 it's more gentle slope. And that's how we show the steepness of a slope on a contour map. Index contours are the thick, bold lines that are labeled. They're thicker and bolder, and they are labeled. That's the most important thing to remember. So, like an index, they are labeled with the page you go to, but here the index contour lines are labeled with the elevation. We also have benchmarks. This is a brass nail that's hammered into the ground. It's about 4 inches across, and it's stamped by the U.S. Geological Survey. In the center is this triangle with a dot, and it says that the elevation of this dot above sea level is 13,796 feet when they measured it back in 1955. And it's the summit, meaning it's the top of this local hill. There's one of these on George Mason University's parking lot. What happened was, when the Geological Survey was originally going around mapping the United States, they didn't want to have to measure all the way from the ocean every single time. So they went to specific locations and recorded that location's exact elevation. So now, if you're mapping in the area of George Mason, you just measure off this benchmark. You don't have to, well, not this benchmark, but the local benchmark. You don't have to measure from sea level, you can measure off the local benchmark. On a map, it'll be shown either with this triangle symbol with a dot in it. It'll say BMX and the elevation, or X and the elevation. Right? Some rules with contour lines. 1, they never intersect, branch, or cross. If they were to touch, it would say that one location is both 20 feet and 40 feet. Not going to happen. You can't have a place be 2 elevations at the same time. So they can't touch. Next, they always close in on themselves, making a circle, closed shape, circle, rectangle, oval, or go off the edge of the map. They can't stop in the middle of nowhere. When crossing a stream, contour lines make a V that point uphill, opposite the water flow. You can check out the little short video to see how that works. Also, concentric circles mean that the elevation is increasing towards the top of the hill. Concentric circles mean circles within circles, unless there are hatchers showing a depression. Depression is a hole, a low area. Hills and holes. Here, we have a hill. We've got circles within circles. If you look at it, it's 10, 20, 30, 40, 50, 60. Our elevation is increasing towards the top, this center. So this is a hill. Notice our contour interval is 10. We are counting by tens. This one on the right is also circles within circles, even more circular than the ones on the left. But notice they've got these weird little hatchers in them. These indicate that this area is a hole. Hill, hole. Again, our contour interval is 10, but we've got a hole rather than a hill. To remember this, are any of you fans of Star Wars? The Pit of Sarlacc on the left here. This is a monster in the Dune Sea in Tatooine. We've got circles within circles, and they've got these nasty little teeth. This is an unfortunate man who has fallen into the Pit of Sarlacc to be digested over thousands of years. And it's a hole. And here we've got a hole with the teeth. Doesn't it look a lot alike? So it can help you remember that these circles with teeth indicate a hole in the ground, like a great big mouth. Some common 3D and 2D views. Here we have a hill. And that's what it looks like on a map. Circles in circles. Here we've got another hill, only it's gentle on one side, steeper on the other. We have another hill. Circles within circles, gentle to the side, kind of sticking out a bit, and steeper on the bottom. Kind of like stairs. Again, when they're close together, it indicates it's steeper. Further apart, it's a gentle slope. Here we have two hills with a lower area between them. It's called a saddle. Two hills with a lower area in between. Here we have a valley with a river. It's higher in the distance, so the river is probably flowing towards us. Ooh, we've even got a little waterfall. Okay. So here on the map, we've got hills off to the sides, and notice the contour lines. When they hit the river, which is shown here by solid, dash, 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 solid, the river points up the hill. So this river is flowing down towards the center, down towards the center. And then here we've got another hill with a couple streams heading towards us. Hill, streams heading towards us. It's higher in the middle. These are called spurs, where the ground sticks out a bit between two valleys. And again, the V's point up the hill. The river flows down the hill towards us in this case. So now here we have a contour map. It's the same one that's in your notes. Got the ocean in the top right corner, the Mere River. What I would like you to do is label all the index contours red. Index contours, again, are the labeled contour lines, typically thicker and bolder than the ones near them. Hills, I'd like you to shade in yellow. For the stream, the Mere River, I'd like you to draw an arrow showing us which direction the river flows. There is one benchmark. Remember where it's labeled with an exact elevation? I'd like you to label that green. On the stream, the Mere River, I'd like you to trace in gray the stream V's, the V's where a contour line hits the stream. And finally, I'd like you to calculate what the contour interval is. When you're done, you can check your answers on the website.